Maintaining confidentiality and privacy is important, and those are some big things that are brought to the table with a virtual private network. When we're sending packets across the network, across the internet, or some other untrusted network, we absolutely do not want just anybody who sees that packet to be able to open it up and make sense of the content. Because if we have secrets that are company secrets or sensitive information or protected information like health information and so forth, we just absolutely shouldn't leak that information or make that available to unauthorized eyes. So to accomplish the feat of VPNs, virtual private networks, as we protect and encrypt every packet as it's being sent over these untrusted networks, we're using some techniques from a suite or a technology called cryptography. And that's what I'd like to chat with you about in this video. So the root of the word cryptography came from the concept of having secure communications in the face of an adversary. So if you had General A, for example, from some army, and you had General B from the same army, and they were going to send messages back and forth, they would use cryptography to make sure that if those messages were intercepted, that the interceptor wouldn't be able to make sense of them. There was some kind of cryptography going on that would hide the actual message that was being sent. An example of this would be a Caesar cipher, as in Julius Caesar. That's what he used. So in the current day and age, cryptography refers to a bunch of algorithms or formulas and standards that can help us to also protect data. But there's two major goals with cryptography. One is confidentiality. In the case of two devices communicating over an untrusted network, if somebody intercepts the packets and they look at them, if they can't make sense of what they mean, the payload, we've just accomplished confidentiality. If only host A and host B can figure out what the actual message is, we've maintained confidentiality with our cryptography. And with virtual private networks, that confidentiality is implemented via encryption. And here's an example using the Caesar cipher of a protected message. And it was encrypted using some type of a key or method. And if host A and host B, or both parties, know what the key is, one can encrypt it and the other one can decrypt it. So the key here is it's a one character shift forward, meaning each of these letters is just one in advance of the actual letter. So if you back up each of these letters, the U would be a T, the I would be an H, and continued on. And if you want to solve this, go for it. Just back off every character to its previous character in the English alphabet, A through Z, and that'll reveal the hidden message. So that's an example of way back when of how we could encrypt a message, and only the sender and receiver who know the actual key or how to decode it could actually make sense of the message. And in today's high-speed networks, what we're going to use is an encryption algorithm, and one of the very popular ones is called AES, which is an acronym for the Advanced Encryption Standard, AES. And then there are several flavors of it as far as how many bits involved. And with cryptography, the general rule is size matters, meaning the bigger the better, or at least the bigger, the more secure it's considered to be. And the more bits that we're using as part of our algorithms, the more CPU and energy it's going to take to do the calculations. So if we had two sites, site A and site B, and they were connected over the internet, and we wanted to implement a VPN between them, we could train these two devices to set up a VPN, a virtual private network. We could tell them to do encryption. We specify the algorithm that we'd want to use. And if we set up this VPN, a question might come up, well, if we're using AES, which is a standard, couldn't just anybody jump in the middle of that with AES and interpret the data? So the secret is these devices that are at the endpoints of this VPN tunnel, they will negotiate and use keys that no one else knows about. So because host A and host B, or router A and router B, have the keys involved, only those two devices will be able to properly encrypt and decrypt the data. While anyone in the middle who eavesdrops on that traffic or wants to look at the data, they're not going to be in luck because they are not going to have the keys. Think of it like a trunk with a padlock on it. Basically, if you have the key to the padlock, you can open it up, you can close it, lock it up. But if you don't have the key, you're out of luck. So host A and host B have the key to that padlock, if you will, and everybody else does not. And that's what keeps our data confidential with encryption using current standards like AES. Now, besides just keeping our data private, we also want to make sure that the data isn't being manipulated or changed by unauthorized parties as those packets are being sent back and forth. And that refers to having data integrity. And data integrity is accomplished through a method called hashing. And we can kind of think of hashing like a little indicator to say whether or not the data has been modified. Think of it like this. Let's imagine I'm sending you this letter. So I've typed up this nice letter, and then I've counted all the characters that are in this letter. And let's imagine there's like 340 characters. So what I do is I take this letter, fold it up, put it in an envelope. I totally forgot what number I said. Let's say it's 425 characters. I'd put the letter in the envelope, close it, and then on the outside, what I could do is I could write a little note, 425, on the envelope. And so when you get it, you open it up, you take a look at it, and we can take just one extra step of saying, okay, I'm going to make sure I count all the characters and then match it against what you said the characters were, 425. And if the number's off, if you said it should be 425 characters, yet there's 450 characters, hey, somebody's tampered with our data. And as a result, we can drop it and not accept it. And that concept of data integrity for an individual packet as we send it over a VPN is referred to as hashing. And for hashing, the two major families for hashing are MD5 and SHA. Now with SHA, SHA, there's a whole bunch of flavors of SHA. Like there's SHA-1, SHA-2, SHA-256, etc., etc. But in either case, the objective of using a hashing algorithm is to verify data integrity, that nothing has been modified or changed in that packet that's been sent over the network. And as a fun example, here's a website, is toolsfornoobs.com, and it's got a hash calculator. I want to help reinforce the idea that the hash is just a teeny little add-on that helps verify data integrity. So I've got the Declaration of Independence in my clipboard. I'm going to right-click and I'm going to paste it in. So there's the Declaration of Independence, and beautiful. So it's got all the words, all the characters. And if we want to generate a hash on this entire document, what we can do is we can select the algorithm. So let's use SHA-256. That's a nice strong one. And then we'll click on hash this. Check it out. See this little teeny thing right here? This hash is based on the entire document. And if we change one character, just one, in the document, that hash is going to change. Instead of unanimous, we'll say majority. Of course, that's changing this document. And if we click on hash this, you'll notice if you go back in the video a moment, this hash is different. So the hash is a teeny little add-on that helps the receiver identify, did this data, did it get messed up or modified in transit, or does the hash match? So in this video, we've had the opportunity to take a look at how a VPN is protecting data. And it's protecting the privacy, the confidentiality, by using methods like encryption. Encrypting the data in a format so that any device without the right keys involved, they can't make sense of it. And the most popular encryption algorithm that we're using today for site-to-site VPNs is AES, the Advanced Encryption Standard. And then to verify data integrity, to verify that data hasn't been manipulated or changed in transit, we use a method called hashing. And the two major categories there are MD5 and SHA, with lots of different variants behind it. But the goal of hashing is to verify that the data has not been modified as it's being sent over the untrusted network as part of the VPN. So now we know a couple building blocks for VPNs. The encryption aspect, which keeps the packets private or confidential, and the hashing aspect, which makes sure the data has not been modified. Let's take those two building blocks and take a closer look in the next video at the site-to-site VPN that's protecting all the traffic that's going back and forth between those two sites. So I'll see you there in just a moment. Meanwhile, I hope this has been informative for you, and I'd like to thank you for viewing.